All right, so it's my great pleasure to introduce our speaker today, Sophia Sanborn, as the recipient of the Faculty of Science Early Career Invited Lecture Award. And as the title indicates, Sophia is an outstanding young scientist whose research focuses on the neural computation of group invariant and equivariant representations. Her work bridges computational neuroscience and machine learning with tools from group theory and harmonic analysis that she incorporates into deep neural networks. Sophia recently received her PhD in computational neuroscience under the direction of Bruno Holfhausen at UC Berkeley, with some previous research experience at Intel AI as well. So over her academic career, she already received several awards and prizes, including an NSF fellowship, but also multiple awards in philosophy and linguistics. She actually indeed received her training originally in these areas, and that motivated her to develop a theoretical framework for the study of perception and cognition. So I just conclude by congratulating Sophia again for the award, and just said that I'm very excited to hear the lecture.
Thanks, very Sophia. Much. It's such an honor to be here, and I've been having such a stimulating visit, meeting everybody, and really excited to hear this group's thoughts on this work and get your feedback and hopefully engage a bit. Just as a preface, I'm very happy to receive questions during the talk, so don't be shy to raise your hand and interrupt me. I prefer dynamic interaction. So yeah, today I'm going to be talking about some of the work that went into my PhD thesis, which I just defended in December. And the problem that I set out to tackle during my PhD is a very old and a very deep one. And let's see, that's not working. And indeed, even Poincaré was thinking about this problem over 100 years ago. And the problem is this. So consider the retina. The retina is a hexagonal lattice of photoreceptors at the back of your eye, and it's catching photons reflected by objects in the world. Now, as you move about the world, the pattern of light that you receive on your retina at every instant changes. When you observe, for example, a ball rolling from the left to the right of your visual field, at every instant, that image is triggering activity in a different set of photoreceptors. And as Poincaré noted, these sensations are conducted to your brain by two different nerves. They ought to appear different in character. So why then do we come to conclude that it's the same object that's being transformed? Our visual systems stitch together this disparate retinal activity into a unified perceptual experience of a single object in motion. So I was very intrigued by how this is accomplished by the brain and what exactly are the computations and mathematics that's being performed in networks of neurons that give rise to perceptual representations invariant to the many transformations of the natural world. These include things like translations, rotations, scaling, changes in lighting. This is what I call the problem of perceptual invariance, and it is core to the goal of object recognition. Now, the canonical picture of how this is achieved in visual cortex goes back to the Nobel Prize winning work of Hubel and Wiesel, who proposed a sort of theory of hierarchical feature extraction and pooling. So back in the 1960s, Hubel and Wiesel were doing work on simple and complex cells. After visual data is captured by the retina, it travels down the optic nerve, it goes into the back of the brain where it's processed in stages in the visual cortex, beginning in visual area 1, which is also called primary visual cortex. So Hubel and Wiesel were studying cells in the primary visual cortex of cats, and they found neurons that could be reliably stimulated by bars that are oriented in particular directions, and these are called simple cells. Now, simple cells are selected for the width and the orientation and position of the bar, meaning that they're going to fire for a bar of a preferred orientation and width, but they will stop when those parameters are changed, as you can see sort of in the schematic diagram on the left. But they also identified another class of neurons, which are called complex cells. And these cells are simultaneously selective for orientation and bar width, but they are invariant to shifts in the position of the bar. So if you translate that bar in the direction that's orthogonal to the preferred orientation, then the neuron will continue to fire. It doesn't mind those minor perturbations. If you change the orientation, it will stop. So we can say that complex cells are translation invariant. Now, these empirical results have been replicated countless times over many, many species. This is really sort of bread and butter of vision science. But computationally, how does this work? So Hubel and Wiesel originally hypothesized that complex cells may work by pooling together the outputs of two simple cells whose preferred positional encoding is translated. And this idea, simple as it may sound, really sets the foundation for what has become the canonical model of neural computation and visual cortex. And the essence of the model is this: through successive stages of computation in the visual cortex, neurons are extracting features that are simultaneously more complex and more invariant than by combining the outputs of stages below. And this has been corroborated by empirical research over several decades. There's a body of data that shows that there are neurons in higher visual areas such as V4 and the inferotemporal cortex that selectively code for things like faces or hands or even novel objects invariant of the position and lighting and other deformations to those objects. But how can we build this capacity into a computational model? So in the 80s, Adelson and Bergen proposed what is now the canonical model of complex cells. So back in the 70s and 80s, it was noted that the behavior of simple cells could be modeled quite accurately as a linear Gabor or Morley wavelet transform. Now, Gabor filter, as a refresher, is a two-dimensional Fourier basis function that has been localized with the Gaussian window. So it's parameterized by spatial frequency and orientation. Now, in vision, we use the term receptive field to refer to the spatial region and pattern of stimulation that maximizes a neuron's response. So simple cells can be modeled as having a receptive field that approximates a Gabor wavelet of a particular orientation and spatial frequency. Now, a Gabor filter, when it's convolved with an image, will change in response as that image is translated. And this is due to the Fourier shift property. So you get a phase change that's proportional to the frequency of each of the Gabor wavelets. And this is what we call equivariance, and I'll return to that later. So this behavior is replicated in simple cells. And Adelson and Bergen's model of a complex cell is to take the outputs of those equivariant simple cells and then to square and sum the output of a quadrature pair of those. Quadrature pair here means that there are two Gabor filters that are 90 degrees out of phase, or you can think about it as the real and imaginary components of a complex Gabor. If you do Fourier analysis much, you might notice that this is essentially a localized power spectrum, since we have preserved only the magnitude and we've thrown away the phase information. And by throwing away the phase, we get rid of those phase shifts that are due to the Fourier shift property. So now we have an invariant. Okay, so this is sort of very classical 1980s canonical stuff. But this model only accounts for the very first layer of visual processing. And if we want to accomplish invariant object recognition, we're going to need more than just translation invariant orientation selective cells. So enter deep networks. This theory really set the foundation for what has now become modern deep convolutional neural networks. This is this idea of hierarchically extracting features and pooling those features in complex cells. This is the original convolutional deep network architecture proposed in 1980 by Fukushima. And this is a figure from his paper, and he was explicitly using this Hubel and Wiesel terminology. He really drew inspiration from their idea of pooling. Then in the first layer, you have these simple features. They're combined by complex cells in a pooling operation. His notation, we then have lower order and higher order hypercomplex cells. Then we have a question mark. Who knows what happens there? Maybe that's V4. And at the end, you get what's called a grandmother cell. This is classic from neuroscience. It's the idea that there's a cell in IT or very high levels of visual processing that encode concepts that are very abstract, like your grandmother. And has been somewhat verified. Interestingly, there's such a thing as a Jennifer Aniston neuron found in a particular patient. So the idea here is in Fukushima's network, now we can't just analytically use Gabor filters. We want them to be learned from data. Ideally, they will learn visually important and meaningful features. So now how do we get the invariance? So the trick here is to take a max or an average operation. And this is what we now refer to as max pooling in modern deep learning. And this has persisted all the way up to today, 40 years later, in modern deep network architectures. So this canonical model has been very, very important in both guiding empirical neuroscience research as well as in constructing computer vision models. But I will argue it's incomplete. Unfortunately, both of these approaches do achieve invariance to translation as well as other perturbations when you're taking a max or an average, but they do so at the cost of selectivity. And to unpack what I mean here, we can just look at the power spectrum. So this is, again, the foundation of the energy model of complex cells. It's very well known in the vision community that the power spectrum discards a lot of important structure in a signal. So indeed, the power spectrum is invariant to translation, but it's throwing away the phase and much of the signal structure is in the phase. And we'll just illustrate that here. If I, for instance, take this image, take its power spectrum, because it's phase spectrum, I'm going to hold the power spectrum constant and just add a random phase and then regenerate the image through the inverse Fourier transform. What does it look like? We've randomized phase spectrum. Here's the image that comes out. We've lost all of the image structure. It looks pretty much like noise. What if we instead hold the phase spectrum from the original image constant and randomize the power spectrum? What do we get? Well, actually, we get basically the original image. Turns out most of the important image structure is in the phase spectrum. And importantly, it's in not the absolute phase, because that's what can be shifted with translations, but rather it's in the relative phase relationships. That's what defines really the important signal statistics. We get all of the edges, the curves, much of what we care about in a signal. So, this suggests it would be pretty surprising if biology, our robust, incredible perceptual capacities were built on such a lossy operation. And indeed, there are empirical studies that suggest that it is not. If you look at complex cells and then you do the same experiment we did here, we just randomize the phase spectrum, those complex cells are going to start giving different responses. They actually have sensitivity to phase structure. So canonical as this picture may be, unfortunately, it's not complete. There's more to the story. And as for deep learning, unfortunately, max and average pooling fare no better. You can sort of just think through it. If you take a max or an average operation over, some image, that is invariant to translation. It's invariant to rotation. It's also invariant to completely random perturbations, right? Permutations, just mix around the pixels and you'll get the same response, right? We've collapsed maybe too much signal information. And we see this issue coming out in the well-known failure modes of deep networks, where they are shown to be excessively invariant. This is a nice paper from Matthias Becke's lab. And here we're seeing two sets of stimuli. So here's the target images in the top row. And they were able to find images, the bottom row, which give the exact same logic response at the output of the deep network. So according to the deep network, these things are identical. But as you can see, they bear very little perceptual or even semantic relationships. So, our deep neural networks are too invariant, but at the same time, it's also well known they're not invariant enough. This is probably the most famous adversarial example image. Maybe some of you have seen it before. If you take an image of a panda that your deep network is confident is a panda, and then you add an imperceptible amount of noise, this is just magnified so we can see it. This is the resulting image. To us, still a panda. Your network thinks that it's a given with 99.3% confidence, right? So the key point here is that our deep networks are not invariant in the right ways. And my proposal is perhaps we should start with the mathematics of invariance and crucially, its basis in groups and representation theory. And if we look back to Poincaré 125 years ago, this is actually what he suggested too. He just didn't have computational machinery or tools from empirical neuroscience, which we have. Now, why groups? Well, in the natural world, variations are not random, right? We actually know a lot about the variations that we're going to see in data. They are highly structured by the geometry and symmetries of the natural world. And consequently, many of the transformations in natural data can be described in terms of the actions of groups. So, a hypothesis that I have been exploring during my PhD is that organisms exploit the mathematical symmetries of the natural world, that the computations performed by neural circuits reflect this group structure, that this is a very fundamental constraint that structures natural signals. And famously, group theory was instrumental in unifying models of physics in the 20th century. I think likewise, it has the potential to unify our understanding of how neural circuits model the world, which is governed by those same symmetries. So my aim throughout my work has been to use this mathematics to first more clearly and accurately define the problem of invariant object recognition, to then provide a set of mechanistic hypotheses for how transformation structure and invariance is achieved through computations in individual neurons, and then to go on and construct artificial neural networks that are simultaneously selective and invariant, respecting both the pattern and the transformation structure, not losing our signal when we build our invariant. So the general structure of this talk, I'm going to first briefly go through a bit of background, a little bit of the fundamentals of group theory that we need for this. And then I will talk about how to build robust invariance in visual cortex, starting from those computational primitives, starting from a deeper understanding of the mathematics of invariant computation. And then I will talk about a project where we incorporate that same mathematics and those ideas into neural networks to build systems that are more robustly invariant. And lastly, I may or may not get to this section, but it's another example of what you can do with this math in neural architectures. In this case, for a hot-field associative memory network, another classic neural architecture. So we'll start here, a little bit of group theory for signal processing. So the question I really want to target here is, what is the mathematical problem that the visual system needs to solve? And I'm going to start by thinking about a sensory image as a map from R2 to R. So R2 being the coordinates, so two-dimensional coordinates, the planes, this is an abstraction, and R is some real scalar value, right? And so that gives us an image, a sensory image, such as these characters here. These are just some handwritten digits from the Omniglot dataset. So crucially, the problem I'm interested in is the orbit separation problem. So you can think about the orbit of an image as the set of transformations on that image. And here we're just showing one-dimensional, horizontal translation. But this is a simple example. So we can generate the orbits of all of those images. And importantly, many of the transformations in images, as I mentioned, are structured by things called groups. So this kind of translation actually forms what is called a group. Just for a little bit of technical definition, here are two simple examples of groups. So we have the integers modulo 6, could be integers modulo n, any you like. And here are the 6 roots of unity, also could be nth roots of unity, okay? So integers modulo n, a group is a set of, in this case, we'll think of them as transformations combined with an operation, which allows you to combine those transformations into new transformations. And crucially, that set operation pair has to meet the following axiom. So the first is closure, which just means if you combine any two group elements, it's also going to be a group element. The second is associativity. So this is really about the grouping. If you put parentheses, A, B times C, that should be the same as A times B times C. Identity means that there's such a thing as a do nothing element, which basically when you add it or multiply it by any other group element, it does nothing. So in the case of Z mod 6Z, that's 0, you add 0, nothing happens. And then the identity element plays this important role that when it comes to the inverse. So with the inverse, that means that there's, for every element in the group, there's an inverse element that undoes the operation, and it gives you back the identity, right? So groups actually give you this really nice way of abstracting away from the specifics of transformations and recognizing the structural similarity between different kinds of transformations that you might see in nature and or in algebra. So in this case, there's actually a one-to-one correspondence between this group Z mod 6Z and the 6 roots of unity, which I should have mentioned, are the complex numbers Z such that Z to the power of 6 is equal to 1. So that's this set of complex numbers. And that isomorphism really is a map from elements of this group to elements of that group. So you can basically find a one-to-one correspondence that preserves the group action. So whatever you would have gotten by doing addition to this group, you'll get by doing multiplication in this group. It preserves all of those mappings. And this notion of a isomorphism, or more generally a homomorphism, brings up an important tool we're going to be using, which is the idea of a representation. So representation is a way of taking an abstract group like the symmetries of a hexagon or things like this, and mapping it to the set of complex matrices. And so it's a map from group elements to complex matrices that preserves the group structure, just like this one here. And indeed, this is actually what you would call a representation for this group Z mod 6Z, because we have mapped our elements to elements of complex matrices. They're scalars, but they're one-dimensional matrices. So this concept of representation we will return to turns out to be quite useful when we're thinking about signal processing. But first, I want to take a moment to now precisely define two concepts that are going to be essential to a mathematical description of sensory perception, namely invariance and equivariance. So Just like we defined our image as a map over R2 to R, we can define our signal processor abstractly as this map phi from the image to Cn. I'm going to assume our representation space is in complex, and n is the dimension of the representation. Sorry, I'm using the word representation in its two forms, as a neural representation or a group theoretic representation. And it's an unfortunate collapse of semantics, but to the embedding space, let's say. So we say that our map phi is group invariant for the group G if phi of x is equal to phi of AG of x for all G and G. Intuitively, what I'm saying here is that applying the group action to the domain does nothing. So my signal is going to be invariant to that. And then we say that phi is G equivariant if, when I apply some group action to the domain of the signal, then there is a sort of proportional, related group action that can be applied afterwards. So basically, if you were to rotate your image and then you pass it through your signal processor, it's the same in some sense, special sense, as if you were to pass it through the signal processor and then rotate. This is our notion of equivariance and invariance. And so if we go back briefly. Yeah.
So how, what's that special sense that alpha G and gamma G are related, especially if their dimensions change?
Yeah, there just needs to be a homomorphism between alpha G and gamma G. So they're not going to be exactly the same group action, but there's a group homomorphism there. Okay, any other questions? Okay, so if we go back to this, just want to point out something fun, which is that, if you do a lot of Fourier analysis and you see things like e to the I theta, you might start thinking about Fourier analysis. And that's because there's actually a really deep connection between Fourier analysis and group representation theory. And that connection is this. The Fourier transform, another way of thinking about it, is that it's a projection of a signal onto the set of irreducible representations of the group of cyclic translations. Okay, and remember we said those z mod n equals 1, z to the n equals 1, these are the representations of that group. And this fact is why the Fourier transform has nice properties with respect to translation, namely that it's equivariant to translation. So as a reminder, this is our classic Fourier transform. And then there's this thing called the Fourier shift property, which when I translate my signal by some z, then I'm going to get out my original Fourier transform times, so I have this times a term, which is just a phase shift, which is going to be proportional to the frequency of that coefficient. Okay? And this is exactly equivariance, according to the way that we have defined it. So another really intriguing fact about Fourier analysis is that you can actually generalize it to other groups. So it doesn't have to be the irreducible representation of translation. It can actually be the irreducible representations of other groups, perhaps other groups that are relevant for perception. And indeed, and here just to explain, rho now is a representation, or is what the representation maps to in complex space. And you can, again, index some special set called the irreducibles of those representations. And now you're projecting onto those rather than your ordinary Fourier bases. And an intriguing example of that is actually to use something like the real spherical harmonics, which are a set of, is an orthogonal basis defined over the two sphere. And these are related to the representations for SO3, the group of three-dimensional rotations. So if you wanted to build a SO3 equivariant map, then you have the tools right here using this group representation theory. And intriguingly, all of this allows us to also build more robust invariance, canceling out that equivariant part. And we're going to get into that now. Any questions before I move on? Okay. Sorry, hard to hear you.
Oh, yeah, G that you wrote.
Yeah.
Any
all compact groups here.
compact groups.
Yes, but can be continuous or discrete. Although I did put an integral there. And DG is a hard measure. Okay, so let's think about how we can use this mathematics in the context of visual cortex and vision more generally as a computational problem. So just going back to our image orbits, I've now color-coded them for clarity. So our goal here is that we want to collapse each of these orbits. We want to send all of those images to the same point in our neural representation space, neural embedding space. So if you pass those images through something like the Fourier transform, and then you do a PCA projection down to 2D just for visualization purposes, this is what you see. And this is kind of the equivariance property in action, right? So you can see that phase shift got projected down, it would be the real and imaginary part. Now we just project it down here. And we get this sort of entangled representation, but where rotation is equivariant to the translation and the input. So if we want to separate these orbits, then what can we do? Well, one easy thing that everybody knows how to do is take the power spectrum, right? We just completely cancel the phase, and then we're able to successfully collapse those orbits. But as I mentioned, you can also generate adversarial examples. This is very small, sorry, but that is, obviously not equal to this character, and yet the power spectrum will collapse it to the same point. So can we do any better? Well, thankfully, there is another object that is built on all of this mathematics and is a simple generalization of the power spectrum, which actually does completely separate group orbits. And it is what we call a complete invariant. And this object is called the bispectrum. And the bispectrum is not only going to collapse those orbits, but it is also going to collapse them distinctly from any other image up to translation. So you can't come up with an adversarial example for this analytical map. Now, what exactly is it mathematically? Here's our Fourier transform. Power spectrum we can get by multiplying the Fourier transform by its conjugate, kill the phase. So the bispectrum is now looking at pairs of frequencies, K1 and K2. So for every pair of frequencies, I'm going to fill out this big matrix. And I'm going to take the Fourier transform at frequency K1, Fourier transform at frequency K2, times the Fourier transform at frequency K1 plus K2 conjugated. And that conjugation is kind of the special little trick that we need in order to get the invariance. And I'll just unpack that in a second. So refreshing the Fourier shift property, we want to understand how does our bispectrum deal with the signal that has been shifted. So I'm going to compute the bispectrum of FC, of X, which means I'm going to have these Fourier transforms, which have these terms out in front, the equivariant bit. So if I just wrote out the the bispectrum explicitly for all of these things, this is what I'm going to get. I'm going to have these three terms up here, and we can just unpack it a little bit more, distributing the K1 and the K2. And you see we have two terms with the negative in the exponent, two with a positive. So fortuitously, those things are going to cancel out. And then all we're left with at the end is just our original bispectrum with the original signal, right? So this is demonstrating that it is invariant to translation. But is it complete? So there is very nice work from Yellett and Iverson that demonstrates that every integrable function with compact support is uniquely identified up to translation by its bispectrum. And so we know, as I said, it is complete in the way that we care about for perception. But how do we implement this in neurons? So going back to this complex energy model of complex cells, we can very simply generalize this. Now we can have a bispectral hypercomplex cell that's going to take the combination, a multiplicative combination of the outputs of three simple cells that bear a particular kind of frequency relationship. Namely, you'll have K1, K2, and then the negative of K1, K2. Sorry, K1 plus K2. Should be noted that I've now localized it, right? So this isn't exactly the bispectrum, this is the wavelet bispectrum, but for neural implementation, we need it to be localized in order to be plausible. Now I use this term hypercomplex here to also refer back to some classic Hubel and Weasel stuff. Back in their original experiments, they discovered not only simple cells and complex cells, but also these strange cells that they didn't quite understand, which were not behaving linearly and certainly not in line with the classic findings. So with simple and complex cells, and indeed with a Gabor wavelet, if you were to show it a bar of its preferred orientation and you just grow it in length, then the response of the cell is also going to grow and it will plateau at some point. Instead, with hypercomplex cells, if you do the same thing, then eventually it's actually going to drop and go to zero. So it has this nonlinear inhibitory thing that happens after a particular threshold. Interestingly, you can actually recover the response if you generate stimuli. So you take the preferred length and then you add negative, the opposite contrast to the edges. And as you grow that, then the neuron's response is indeed going to grow in line with the classical picture. So it seems like there's sort of like an inhibitory zone in the receptive field here, and you can get around that by negating it. Hubel and Wiesel originally interpreted this as these cells as being length selective, because they prefer a particular length, but maybe there's another explanation. So intriguingly, if you build this, bispectral hypercomplex cell model, and you show it a bunch of bars of different orientations and lengths. Sorry that the plot is so small. The colors are cycling through length, and the x-axis is cycling through orientation. You find that they're selective for a particular orientation, just like the classical hypercomplex cells. But intriguingly, they have this exact same end-stopping effect. So as you grow the length of the bar, eventually it shunts down, and you sort of suppress the neuron's activity. And then we can try that sign of contrast thing. If we change the contrast in the edges, then indeed you can get it to recover and grow in response here. So this is just a bit of suggestive evidence that perhaps, this nonlinear bispectral model could be explaining some very classic findings that we see in the literature. It is only suggestive, but intriguing and perhaps worthy of further investigation. Yep.
Build in the complex conjugate here, okay, too. How does that?
Yeah. So when we're modeling simple cells in visual cortex, people usually don't think of them as being complex valued. You have a sort of real and imaginary part represented separately. So basically, the conjugate is just going to be like an imaginary one, the negated, and that will be the you negate basically the conjugate. If that makes sense. Okay. So as I mentioned, there is this generalized group theoretic form of the Fourier transform. And what I find further interesting is that you can, of course, also generalize the bispectrum, which is built on the Fourier transform. And now you can get a generalized group invariant bispectrum. I should note that this is the form here. So now rho is a representation, right? Representation may be spherical harmonics, although in this case, this is the commutative form. It should be noted that the representations of commutative groups have a very special property, which is that they're all scalars, one-dimensional. But when you go to non-commutative groups, now your representations are matrices. And so you have to have a different form. It's a little bit gnarlier, but it works out just the same. This is the Clebsch-Gordon decomposition, for those who know. Basically decomposes a tensor product of two representations into a direct sum. But still doable, and we have a general form for both commutative and non-commutative groups. And Caporala is the person who really pushed this work on the generalized group theoretic bispectrum, and it also found, was able to prove that, generalize the results of Gillett and Iverson and prove that every integrable function with compact support is uniquely identified up to group action by its bispectrum defined over any compact group. So this stuff is really general. The bispectrum is providing a unique and universal sort of signature of signal structure up to group action, up to some arbitrary transformation. Yep.
Is there actually an easy format to reconstruct the function from its bispectrum?
So there's been a lot of work on this, and some people have come up with algorithms for doing it, so it is doable. And I haven't personally dealt with any of them, but I know that it exists. Of course, you've thrown away the transformation, so you have to add in an arbitrary phase at the end. Okay, and before I leave this section about robust invariance in visual cortex, I just wanted to sort of suggest that, the way that what this picture evokes to me is potentially a more general framework for thinking about what simple and complex cells are doing in visual cortex. That, Gabor's simple cells, they've been around forever. People have given them many explanations, sparse coding, frequency, analysis. But potentially what they're doing is that they're the localized forms of the irreducible representations of the group of translation, and that they are trying to preserve equivariantly that transformation structure so that it can be used downstream to infer, where things are translationally, as well as nicely canceled out so that you can have robust invariance. And it suggests that potentially we might expect to see in visual cortex more exotic receptive fields related to groups like SO2 and SO3. There's some evidence for that, but I won't go into it here. It's really future empirical work waiting to be done. But the main takeaways here are that the bispectrum provides a complete characterization of pattern structure while factoring out group actions. There is a somewhat natural biological implementation, and that model replicates both sensitivity to phase structure as well as the extraclassical receptive field properties associated with hypercomplex cells. Then lastly, it can be formulated for arbitrary compact groups, thus providing a framework for generalizing simple and complex cells in visual cortex. Okay. So going from here, as a computational scientist, I'm very interested in making use of these ideas and this mathematics to now construct artificial neural networks with improved robustness. So now we're going to move into one and maybe two projects in which I demonstrate how this can be done. We're going to start by learning robust invariant maps with neural networks. So again, we're starting with this analytical form. So the strategy I'm taking here, start with the solution that you know exists, and it turns out to be neurologically plausible. Now let's remove some constraints. So in a machine learning context, we don't want to have to build it in by hand. We also don't want to have to maybe know the representation theory for every group that we possibly want to be invariant to in our neural networks. So what if we, instead of the Fourier transform explicitly defined, parameterized it with a weight matrix? So the Fourier transform is just a linear transformation. It's a projection. You can have this DFT matrix and you just take the inner product with your signal. So we can, instead of the DFT matrix, just replace it with a random matrix that we're going to now optimize in a machine learning setting. And this first network architecture I'm proposing here, this sort of has the most structure built in. So I took out the weight matrix, but I'm keeping the sort of what we have marked here as beta, keeping the bispectral indexing trick. So we're going to do the K1, K2, K1 plus K2 thing here. Okay, and this is called our full bispectral network. So we take a signal X, we multiply it by weight matrix W, we do this fancy indexing, we get n squared coefficients, which by the way is more than you need. The bispectrum is highly redundant. You only need n divided by 12 for a real signal, but we just have it complete here. And that gives you our full bispectrum network. Alternatively, we can make use of the fact that the bispectrum is highly redundant and you don't need all n squared to approximate it with a different form. So noting that it's basically the product of three linear forms, you can form a network where you have three weight matrices, and you're just going to take the Hadamard product of the outputs of those three weight matrices. So what we have in our bispectral approximate network is ux times vx times wx is going to give our output dimension n. And what do we expect here? So if we were to compute an analytical translation invariant classic bispectrum, U, V, and W should all be variations on the DFT matrix. Let's say U would be the original. V is going to be a permutation of the rows because you need to pair different frequencies with each other. And then W is going to be basically U times V conjugated. Okay, so that's what we would expect if we were to learn the analytical bispectrum. So with these neural architectures in hand, what I really want to understand is, can we learn a bispectrum? Yep.
Are the size of the network different? For instance, is W bigger than when you're?
No, they're all equal size.
Mhm. That's sufficient.
Well, we'll see. We'll have to see what happens. So yeah, can we learn a bispectrum? So the problem that I'm starting with here in experiment 1 is the simplest form supervised learning problem. And what I'm getting at here really is, what can you compute with artificial neural networks? Everybody knows about the universal, function approximation property of deep neural networks. In theory and in principle, you should be able to compute, any function with the deep neural network of arbitrary size. But what about in practice? We don't want infinite width networks. We don't want, infinitely many layers. So the strategy I'm taking here is building in a little bit of structure, changing the computational primitives. Now we have something that's third order and is complex valued. And I'm going to compare it to a generic network and see, okay, can you learn a bispectrum with a generic network? Do you need these computational primitives? Maybe you don't. We'll find out. But here we're going to have a supervised learning context, right? So I'm going to have some synthetic data. They're random IID Gaussian signals. Each row here is a different data point. And then you have all of its different cyclic translations going down. So this is what you call orbit 1, orbit 2, and orbit 3. And of course, there's more than that. We use 100 classes typically for training. And the network needs to learn the mapping, which is X goes to its bispectrum. We analytically compute its translation invariant bispectrum. Can it learn that map? Okay, so we first look at ReLU-nets, and I'm going to vary many parameters, many different numbers of layers, different numbers of weights, and just try to see if I can get it to learn this map. So what we can see here on the left is the training loss. So training wise, it's fitting to the data, right? It's able to learn that map. But then when you look at validation loss, which is the really critical thing, this is data that it hasn't been explicitly trained on. It can't get below a certain threshold around 0.5 mean squared error to the analytical bispectrum, which has been unit normalized. So this is quite bad. This is our best ReLU-net. Okay. And should note, I'm ranging from 3 to 6 layers in the network and going up to 800,000 parameters. Yeah.
I didn't understand the learning task.
Mm-hmm.
What's the input and output?
Yeah, so the input are these data points. Each one is a vector. You just have a bunch of random one-dimensional signals, okay? And the labels are the analytical bispectrum of each one of those data points. So all of the things in orbit 3, they have the same label, which is the big old raveled vector, which is its bispectrum. Does that make sense?
Yeah.
Okay. So that turns out to be really hard to get generic ReLU-nets to do. I have 800,000 parameters in the largest one here. But when I now use my bispectral architectures with certain kinds of ansatz, computational primitives built in, then we do quite well at the task. How do we know what it's learning? We can, for instance, look at the weights. This is what we get out of the full bispectrum network. And as you can see, it is a close to perfect DFT matrix, if you're familiar looking at those things. But each one of these is the sine wave, one-dimensional sine wave with a different frequency. Each row is a different weight. And if you look at the power spectrum, each one is pulling out a different frequency and is selective for those frequencies. Okay. I didn't constrain it to be unit norm, so you get different power on each one, but it's approximating now a Fourier DFT matrix. Yep.
So if you do an ablation study where you remove some of these modules, does it fail?
Models or?
Just thinking about your bispectrum network.
Oh yeah, that's a good point. So what we're looking at here is the full network. So I only have one weight matrix and then I do the special indexing. But when you use the UVW, I have done experiments where you take out one, like let's try to just do it with 2, U times V, and indeed it fails. So it seems like you need the 3. Okay, but this is really just a warm up. I just want to see, is there any value to actually using a different neural architecture with this kind of form? Looks like there is, but the problem that we really want to get at actually is a very hard problem. Given a data set with unknown latent group structure, can I infer its group and thereby learn its representations? Okay, so it's not going to be supervised learning anymore. Exactly, it's sort of semi-supervised, and ideally we'll go even less supervised. We'll talk about that in a second. But what we want to look at here is, I don't want to have to know the group. I don't want to have to know the representation theory. What about other groups that are relevant for perception? I'm going to do ones that are relatively known, but ideally, in the future, we'll apply this to more exotic groups that we might not even understand. Okay, but we're going to start with translation again, and then we'll go to 2D rotation, SO2, and then 3D rotation, SO3. And to put this into a semi-supervised context, really mirroring the orbit collapse problem, the point is that I know that some things are the same, but I don't know how they're the same. I don't know how they relate to each other. So I know that, basically all of those things are the same character, but I don't know in what way they are related. And so to set up this problem, we're going to use the bispectrum module combined with a contrastive loss. Contrastive loss has been used in deep learning since this paper from Hatzell et al. And the basic idea is if you're trying to learn an embedding space for some signals, you want to bring things that are deemed to be similar closer together in the embedding space and push things that are deemed to be not similar farther apart in the embedding space. So your loss function has 2 different terms. This one is going to be used when examples are similar. You have this y, which is an indicator function of whether they are similar or not. And so if they are similar, your penalty is going to be proportional to the distance of distance of those 2, because you want them to be close together. And then if they are different, then your penalty is going to be the maximum of either 0 or the m, which is the margin, minus the distance of those 2 points. Okay, so you're basically going to get penalized when the different points are below a margin, and also when similar points are too far away. Is that clear? So starting with cyclic 1D translation, again, we use this data set. And now we're going to just be looking at the approximate network because we don't want to build in too much structure. So we have a UV and W matrix. This is what comes out of the bispectral network. And as you can see, they are pretty good approximations to a DFT matrix with some exceptions. Some of the weights kind of tend to go to 0 and end up being trivial. This is our best performing ReLU network. Intriguingly, you actually also learn DFT bases, which is quite interesting. And suggestive that, when I've put so many constraints that I was forcing it to get the bispectrum solution, it wasn't performing. But when I loosened up those constraints and allow it to find any solution to solve the orbit collapse problem, it actually does learn a solution. And intriguingly, it learns a Fourier-based solution, right? There's nothing about the Fourier transform in there at all. It's just that I translated images, right? But these representations of that group pop out naturally by trying to solve the orbit collapse problem. It suggests something about the universality of these features. So let's probe a little bit deeper into what these networks are actually learning. When we look at the bispectral network, is it actually learning the bispectral map? If it is, then these three weight matrices should have a very particular relationship, right? The frequency relationship that I mentioned, this is probably too small for you to see, but all of the ones that are in red actually have that frequency relationship. The ones where it's not typically correspond to these trivial ones that ended up going to 0. And that might reflect something about the difficulty of optimizing a complex valued third order network. It's pretty exotic, not typically done. We can also understand this network better by looking into the network outputs after the first and last layer. So after the first layer, we expect it to be equivariant. Remember, if it's Fourier transform. And indeed, what you get is as we translate input, I compute activations on all of these different coefficients. Right, and each one of these colored lines refers to a different neuron. So what we end up getting is basically what you expect from the output of a Fourier transform. It is equivariant with a phase shift proportional to the translation. I'm just picturing 3 neurons here. This is the output. It's very robustly invariant. When we now go to the ReLU network, what we get is basically a rectified equivariance, as you might expect. So everything that's below 0 gets put to 0. So you kind of get these 2 bumps. It's a little bit noisier, and the output is also noisy. We can also look at how these networks generalize to completely unseen novel data. So I'm always using random data. I'm just going to generate a bunch of new random signals it's never seen before, and their orbits with translations. And then we're going to compute the pairwise distances of those embeddings in the embedding space and see, did it collapse all of the things in the orbit to the same point? So we're looking at distance matrices here, and each row, which is really, really small, actually corresponds to a different point. And then this grouping corresponds to everything that's in orbit 1. So if the networks are working, then you should see a block diagonal structure like we see here. Both of them do a very good job at generalizing to completely novel data, which is quite cool. But we can unpack a little bit more what's going on here. Here I generated adversarial data by phase scrambling. So I preserve the magnitude, but I phase scramble to kind of get at it, are either of these networks doing something more power spectrum like? We know that that's a solution. Maybe one of these networks has found that. And if it were fooled by these adversarial orbits, then it would, again, collapse them and give you a block diagonal structure, kind of like this one, right? The bispectrum network is not fooled. It basically collapses orbits that are right at chance for the size of the number of data points. But here for the ReLU network, we end up getting a substantial amount of orbit collapse. It's not completely collapsing those orbits. It's not exactly computing a power spectrum, but intriguingly, it's clearly losing some of the important signal structure because it's managing to be fooled by those scrambled phase data points. Another question I want to look at is how do these representations behave under noise? So in this case, I'm going to take, again, novel data, and I'm going to add different amounts of Gaussian noise, sigma 0.1, 0.2, 0.3. And then this is sort of the success at collapsing those orbits for the bispectral network. No problem, bispectral network is managing with that just fine. But here's where you really see these networks start to differentiate. So the ReLU network actually really starts to break down. We ended up getting misclassifications 35% of the time for noise of sigma equals 0.2, and quite poor performance, mostly wrong for 0.3. Okay, we're actually really kind of short on time. So I'm just going to quickly show results from the other groups, and then we can stop for questions. But when we look at SO2, similarly, I generate random signals. These are sums of Fourier plane waves, and then I take their orbits under SO2. What do you think the networks learn? Well, in this case, this is what the bispectral network learns, which is quite interesting. These are basically linear combinations of the Bessel, normal modes of the Bessel functions or the harmonics on the disk, which are intimately related to the group SO2. So it's very nice to see those popping out here. And as you can kind of visualize in your head, you can see how these are equivariant to rotation, right? So as you rotate an image, the inner product with this filter is going to be equivariantly phase shifting, and we'll see that in a second. The Rayleigh network, on the other hand, learns this because this kind of works well enough. Basically, the invariant solution, these target patterns. So these are also going to be invariant to rotation if we design them right. And so, maybe that works well enough. Let's see. So we can see the equivariant response of those bispectral filters here and the invariance of the output. But with the Rayleigh network, we actually, as you might expect, get invariance and invariance. Okay. Does it work well enough? Here is, I'm actually going to generate now to new data, to sort of real data. It's omniglot, handwritten characters. I want to see if these networks trained on random signals can generalize to this. Turns out that both of them do a very good job, 99.8%, 98.5%. But again, they start to get teased apart with the addition of noise. So SO2 bispectrum network does fine with noise. The Rayleigh network really breaks down. Again, this is getting at the point that, of course, there's an invariant solution that exists that the Rayleigh network learned, but it is not a robust invariant, and it is susceptible to the kind of perturbations that you can fool a deep convolutional neural network with. Lastly, SO3, this is just a little teaser. I haven't completely finished this experiment, but if you, again, generate random signals now defined on a sphere and the orbit by taking all rotations of those signals, and then you feed it to your bispectrum network, I wanted to see if the network would learn spherical harmonics, because that's what you expect, being the representations of the group. And indeed, you get filters that pop out of the network that look like this. For those who aren't familiar with this way of plotting, what we're doing is the magnitude of the filter or the signal is the distance from the origin. And then the color indicates positivity and negativity. So often the spherical harmonics are plotted like this. Is sort of another way of seeing structure of a signal on a sphere. But intriguingly, these are approximations of some of the spherical harmonics. This is obviously just a subset of the weights under the network, but the trend holds. And you also get the nice equivariance property out of the first linear form and invariance at the output. And it generalizes quite well to completely novel data, novel functions on a sphere. So the real takeaways here, first is that computational primitives really do matter, especially if you care about efficiency. So the bispectrum ansatz gives us up to 100 times parameter efficiency. I forgot to name the parameter, sorry, but for the first example, it was 800,000 versus 8,000, right? 100x reduction, not in all cases, sometimes it's less, but that was our best example, as well as robustness to noise perturbations. Second point, canonical objects from group representation theory emerge from solving the orbit separation problem in a machine learning context. I think that's a really deep thing. If you've looked into deep networks at all, you might see that there's certain kinds of features that seem to reappear over and over again in the first layers of deep networks. And they also correspond to features that we see in early primary visual cortex. And I think it's not an accident. It's because there's something really canonical there. There's a canonical problem that these visual systems, artificial and biological, are trying to solve. And there's canonical solutions to those problems. And so I think that math can give us a really good guide to what to look for. And lastly, sort of said this in the last point, but if these are indeed universal solutions to the problem, we might also expect them to emerge in biology, just tying back to the previous section. So I think we're out of time. I have a third section, it's about Hopfield networks. And if anybody wants to ask me questions about it, I'd be happy to take questions and discussion, but I will now open the floor. But not before thanking my collaborators. Christian Shoemake, who is a graduate student at Berkeley in the Redwood Center, Christopher Hiller, who is a former Redwood Center alum, but now running a computer vision company, and Bruno Olshausen, my PhD advisor and professor of neuroscience at Berkeley. Anyway, thank you so much for your time, and I look forward to hearing your questions. Something in the chat. Firstly, oh no, nothing. Yes, Manu?
In your, first of all, really cool.
Thank you.
Somewhat in your in your learned bispectral network, why do you find sine waves and not linear combinations of sine waves? So those are just as bad as Fourier basis, right?
Yeah, it's actually a really good question. I don't know. I would expect maybe to also sometimes see linear combinations. I will say, like when we do SO2, we do see linear combinations of disk harmonics. For some reason, the Fourier basis seems to just pop out, but I'm not sure exactly why. I agree that that is also a valid solution. Other questions? Yes.
It is obvious from some perspectives presented, but I was wondering, like, do these bispectral networks that we talked about before, do they have that much practical use for object detection in real world RGB images? It seems like they amazing, but
Yeah, so that's a really good point. So everything I've shown you thus far has been with synthetic data where there's a single group acting globally, right? And this is a very contrived context. And I started with this point to kind of, so that I can sort of get the easiest problem first, and then we can move towards real data. And in real data, what you have is hierarchical compositions of groups that are acting locally on parts of objects, as well as whole objects, as well as scenes, right? It's a much, much, much more complex problem. And in addition to that, you also have all of these sources of information collapse. For instance, the real world is three-dimensional, so there's SO3 acting on 3D objects, but then the image is a two-dimensional projection, so you lost all the information on the backside. There's, it's not actually the group SO3 anymore that we're getting. It's, the group may be in some latent space, and then we have projection. There's also occlusions, right? And so I can't, now this is like kind of ruining my perfect group acting on objects picture. So, this is the direction that we're moving towards. The first step in that is making it convolutional, aka localized, as well as hierarchical. And there's also some theoretical work to be done, understanding how to combine bispectra for hierarchical groups and how those groups are going to sort of hierarchical compositions of groups will come out in the bispectrum. But that is ongoing work, and that's what's necessary to take it to real world data.
I have a question.
Yeah.
In the Zoom chat.
Yeah.
Arturo Beza asks, is there a way in which you can find specific noise that makes the bispectral network do worse than the ring networks? And clarify this so it's something adversarial for the bispectral network, but it's not bad for the ring network.
That's a great question. And also, hi, Arturo, nice to hear from you. Yeah, so this is another thing that I want to do. Which is to generate adversarial examples in a way that's maybe more like how people do it typically in deep learning, which is you actually backprop to find the stimulus, which is going to maximally confuse your network. And I haven't done this experiment yet, but are very excited to basically doing that for both bispectral networks and ReLU networks and try to see, what emerges there. Just analytically, I'm not sure that I can think of a way to come up with one that would be worse for the bispectral than the ReLU networks. But yeah, that's kind of, we really want to dig deeper into understanding the underlying structure in these learned spaces in that way.
Thanks, Sophia.
All right, I also see something from Tim Strabinger in the chat. If I recall correctly, adversarial examples for convolutional neural networks are often found by numerically optimizing over images. Yes, indeed. What sorts of images do you see when doing the same adversarial techniques here? So you're preempting me. And yes, I haven't done it yet, but I am looking forward to doing that. And the interesting thing, what you would hope for a perfect network, which is probably not the bispectral network. But what you would hope is if you tried to generate adversarial examples, by the way, typically you're maximizing the mean squared error between the example and then the thing that you've generated, right? So translated versions of the same image have very high mean squared error. So you would hope that if you have this like network whose latent space is capturing the topology of that group, then the adversarial examples would just be translated versions of the digit. That would be cool to see. I'm not sure whether that's going to happen for either of these networks, but that's the kind of thing we want to look at. Are there other questions in the audience? Yes.
You insisted very much that the groups need to be compact.
Mhm.
What about, so you actually mentioned translation, which is not, or
Yes.
Lawrence group, which is basic in
Yeah.
in physics. So how would you approach this non-compact?
So with translation, I was always using cyclic translation to make it compact. And all of the sort of math of the Fourier transform is built on that as well. The reason why I keep emphasizing the compactness is just because all of the results have assumed that in order to make all of the proofs and claims. So if we want to say that it's indeed complete, a complete invariant up to the group action, then we need that, at least for the proofs that have thus far been put forth. It's a really good question of whether you actually need that in practice. And so, from a sort of engineering side, we can just kind of try it and see, perhaps you would actually learn something meaningful. Perhaps you only need that for these, sort of analytical guarantees, but in principle, you can get far enough with this. Yep.
There's another question on the chat.
Great.
From Dave Baldwin.
Mhm.
It says, I believe humans are worse at recognizing faces when the faces are upside down. What could it mean to leverage equivariance but not rely on it completely?
Yeah, thanks for the question. So this is an important point that I probably didn't make totally clear. Invariance is not the goal of vision. It's maybe the goal at the very end for certain tasks when you need to say whether this is a cat or not. But you really, really need to preserve the transformation structure all the way up the hierarchy. And indeed, our brains retrieve information from all of those different levels in order to answer certain kinds of questions, like where is this thing going? Can I extrapolate the trajectory of this object? And then there's a whole, sort of statistical adaptation side of it. So when we say that our representations of objects are invariant, they're invariant to the statistical transformations that are meaningless, that don't matter for our behavior, right? For instance, you can say that an apple is an apple when it's green, yellow, or red. You're not confused, right? You're somewhat invariant to its color. With humans and face recognition, there's a well-known example in neuroscience that humans have a really hard time telling who is who when the face is upside down. And that's because, the statistics we get, we never see upside down faces. So we're not totally rotationally invariant to that. So there's this important interplay between statistics. We sort of have distributions on groups, right? And you kind of need invariance over some distribution, not complete invariance. And this is another aspect of the complexity of the story when we get to real world data and actual neurophysiology. Thanks for the question. Any other questions in the room? Yes.
Thank you for coming.
Oh, wow.
Congratulations on the BBC Early Career Award.
Oh, thank you so much. This is a great t-shirt.
Thank you for coming.
Thank you so much. Really appreciate it. All right. And I'll be around if anyone wants to chat afterwards. Happy to talk more. Goodbye to the people on Zoom. I'm going to log off.